Hello, this is Dr. Alberg, and I'd like to welcome you back to our course, Introduction to Reinforcement Motion Control. The topic of our lesson today is the current PID system block. What we see over here is the tool which I developed about 10 years ago, which shows the PID block diagram, model, simulation, and tuning. The block diagram, which is shown over here, is showing the state, the system that we try to control. The control itself, which in this case is PID. PID is have a signal output which is translated to a force or torque that applied by the motor on the state. And the output, according to Newton's second law, is force equal mass times acceleration is acceleration. We integrate the acceleration twice and we get position. The position is being fed back, and we get over here the summation junction where we take the reference signal where we want the output to be, subtract from it the actual position. The difference is the position error, which is being fed into the PID controller, multiplied by the proportional, the integral of it, multiplied by the integral gain, and then the derivative of it by the derivative gain. The model is very simple. The mass actually with the spring and a damper where the force is being applied, the result is position. The parameters of the stage are being placed on these boxes, including the mass, stiffness, and the damping coefficient, including motor constant, which interfaces between the PID low signal, which goes into the amplifier. The amplifier amplifies it with higher current, which results in a force. So we define it as Newton per amp motor constant. Over here, we have the controller parameters, the proportional, derivative, and integral, including a set point where we want, when we tune the system, the position of the output to be. And we define it over here in meters. This is the reference that we apply a step function, and we see how the system responds as a function of time. In the bottom, we see charts which are called frequency response. The frequency response shows the gain, which is the ratio between the output and the input, amplitude as a function of frequency, and also it shows a phase diagram, which is how much is the output lagging behind the input. We have frequency response also for the PID. In other words, if you put an oscillating signal over here, what will be the output of the PID controller? And if we combine the two, literally by algebraic summation, we get the open loop frequency response. Now, the open loop frequency response has a very interesting parameter, which is called the bandwidth of the system. And when we look at the closed loop frequency response, where we put the input over here and the output over here with the feedback itself, then we see the same bandwidth as we saw over here on the open loop. But we see that between the very low frequency all the way to the bandwidth, the error is literally zero. In other words, the gain is equal in dB is equal to zero, meaning that the output equals to the input. However, when we go in frequency beyond the bandwidth, then the amplitude starts to decay in amplitude, and the reason is because it is too heavy or too damp to really respond. So the frequency is running and the output is staying still. Now, what I like to do now is take a look at the example over here of the tool itself. We see over here all the variables. We can try to tune it, and this will be part of the exercise that we'll do in homework. But if, for example, we change the Control parameters, adding a 0, increase them by 10, factor of 10, all of them based to the reference. The objective is to decrease the settling time, and if we run it, then we see that if it was before 150, now we tune it a little bit, it is less than 100 milliseconds settling time. So with that, I'd like to thank you for listening, and I look forward to see you in our next lecture.